All right, so now let's get into the our first radical reaction here, which is halogenation. Okay. So what do we see? So just start on, again, the importance. If you're going to break these into the most important steps before you get into mechanism, stereochemistry, anything like that, it's what's the substrate, what are the reagents, and what are the products, right? So in this particular example, they're using methane and using then chlorine gas in the presence of light to generate methyl chloride. Okay, importantly, we have an alkane that we're converting to an alkyl halide. So hopefully some like alarm bell kind of things just went off as to why these are important. First of all, we've never been able to work with alkanes before. So this is the first set of reactions that we have that we can actually work with just a naked old alkane that doesn't have any special functional groups or anything like that. And then we can turn it into an alkyl halide, which we know how to do a lot with at this point, right? So this is the real root of why these radical reactions are so powerful. Convert an alkane to an alkyl halide. Okay, so first step in all radical reactions is initiation. You got to create the actual radical. Again, that's what the heat or the light, in this case, it's given to us as light, but that's what it's doing, is helping to homolytically cleave that bond, creating our two chlorine radicals. Okay, and again, that is our homolytic cleavage, that initiation step. So now we got two chlorine radicals. These are what are going to go on and react with the alkane. So how does that happen? So the first step is this hydrogen abstraction. Okay, kind of different from what we've seen before. The chlorine is not going and immediately attacking this carbon. It's actually plucking off one of these hydrogens first. Okay, so what we see first is a hydrogen abstraction where the bond between carbon and hydrogen is broken and a new bond between hydrogen and chlorine is formed. And again, importantly, that bond is broken homolytically. So this creates this, in this case, it's a methyl radical, but nonetheless, it creates a radical on the carbon. Okay. This would be a propagation step, right? Because on the reactant side, I have a radical, and on the product side, I have a radical. So that's a propagation step. So then what happens next? This guy doesn't just stay like that. It's also highly reactive. So it's going to react with a molecule of chlorine gas that hasn't yet been homolytically cleaved, right? So it can go and now do this halogen abstraction, where a new carbon halogen bond is formed and a halogen radical, or specifically a chlorine radical, is formed. Okay, so this would be the halogen abstraction. But that's how we go from having this carbon hydrogen bond to now this carbon chlorine bond in these steps, both of which are propagation steps. Now, note that certain things appear in both steps, and thus I can cancel them out, right? I have a chlorine radical over here and a chlorine radical over here. Likewise, I have this carbon radical over here and this carbon radical over here. By crossing these out, I get the net equation, or what my net balanced chemical equation, which is that the methane is reacting with chlorine gas to form that methyl chloride, or that alkyl halide, as well as HCl. Okay, but the reason why if you need to do the mechanism, of course, you got to consider all those. But when you're writing a balanced chemical equation, you get to cancel stuff that's on both sides. So this would be the net reaction. Okay, and then the last step that has to occur is the termination step. And this happens anytime two radicals find one another. Whether they both be chlorine radicals, they would find one another and form a new covalent bond, you know, that's that coupling reaction. You can have a methyl radical find a chlorine radical. That would form that new methyl chloride bond. But importantly is it would stop the reaction. You wouldn't generate another highly reactive radical species like you do in the propagation step. Or you can even have two methyl radicals finding one another and thus coupling and stopping the reaction there. This is going to be by far the most common one. We'll talk in a second about concentration, but the concentration of the chlorine is much higher than the concentration of the methane. So this right here, like, be a good way to synthesize ethane from methane or to form new carbon-carbon bonds. By far the most stable radical, the radical that's probably going to be the highest in concentration in solution, is going to be this chlorine radical. So that first one is the most likely event, and that's kind of the one that we consider happens. We assume happens the most in solution. Okay, now, because of the nature of this mechanism, there's nothing to stop it from going again and again and again. In theory, you can have as many chlorinations as you have hydrogens, right? There's no way to really stop it, because this species here, this methyl chloride, is pretty much just as reactive as the methane to the carbon. To the chlorine, and specifically the chlorine radical. So if you let this reaction sort of go unchecked, you will end up getting just full chlorination all the way to the carbon tetrachloride. So most of the time, that's not what we want to do. We don't want to get full chlorination. So what we do is we just make sure to have an excess of methane relative to the chlorine, and then we can ensure that we get the methyl chloride, right? So we only want this guy here. And we can do that by just making sure that the concentration of methane to chlorine, there's much more methane. That means that we'll have to separate out the methyl chloride from the methane, the unreacted methane, but that's much easier to do than separating methyl chloride from, say, methylene chloride. Okay. It also means, just logistically, you can stop it, you can use this technique to generate methyl chloride pretty easily. There would be no way to sort of generate methylene chloride without having a huge amount of contaminant of methylene chloride and chloroform, which are, again, really hard to remove. So our goal is to stop. The goal when you're doing these reactions is to have it stop at that single addition step, the monochlorination. All right, so now what about stereochemistry, right? So when we have chlorine and, let's say, butane as opposed to methane, now all of a sudden you have this sort of idea of regiospecificity as well as stereospecificity. Regiospecificity we will specifically talk about in this next lecture that's coming up. So we're going to focus on stereospecificity first, okay? Obviously, if your chlorine adds to this terminal carbon here, you don't have anything to worry about because there's no stereoisomers that are. But if your chlorine adds to this secondary carbon here, then all of a sudden you've generated a new chiral center. And that just begs this question of what the heck is going on in terms of the stereospecificity. Well, again, the good news, if you remember what I was telling you before, is that we consider, and again, let's simplify things. And instead of doing this complicated one, we're just going to say it's trigonal planar. Because the methyl radical is this trigonal planar, that means approach from either side. And so the bottom line is you're not going to have any stereospecificity. If you've generated a new stereocenter, so for example, the chlorine attacks here, I've generated a new stereocenter, you're always going to get a racemic mixture or a 50-50 mixture of each stereoisomer. Okay, so in this reaction here, if I asked you to show me all products, including stereochemistry, you would just always make sure to give me both the dash and the wedge for each product that's formed that actually has a stereocenter. Okay, so yeah, again, good news, not stereospecific, so you just give me all stereoisomers that are possible. Same thing when you start with a chiral center and then you have a reaction. In this case, it's bromine. And again, we'll talk a little bit more about bromination versus chlorination in the next lecture. But if we have bromination on this particular chiral center, we have then generated a new chiral center, okay? But again, we're going to say that this is not stereospecific at all. So actually, if I had asked you for all the products, including stereochemistry, what you would have done, is just made sure to give me one structure where bromine was on the wedge and the methyl group was on the dash, as well as another structure where the bromine was on the dash and the methyl group was on the wedge. You're always going to get that racemic mixture, again, because that radical, when it forms, is just completely flat. So the incoming radical can attack from either side and does so without any sort of bias.